Welcome back to the 20th video about my full fly-by-wire electric outboard project. 3 weeks ago we revamped the front end of our ADC and the results were abysmal. Card here, link in the description. Then we spent 2 weeks chasing noise and intermittent errors in our circuitry. 2 more cards here, 2 more links in the description. Today we will hopefully be able to reap the fruits of our labor. So enjoy! I also improved the code for calibrations a little bit. One viewer at one point remarked that I really should copy my data from the serial monitor into an Excel spreadsheet and do a proper analysis. I won't do that because I'm too lazy for that. Instead, I added the required analysis functionality into the code. And it's all controlled by this macro calibration. If that is defined, something magically happens in the loop. First of all, I have here a constant calibration set, currently 2048. That's the number of samples I take for a calibration. Accordingly, I have here a static array, a calibration data, with the size of my calibration set, and another static variable, a calibration sample, that's my actual pointer into that array, which is initialized to 0. And here in the block where I take my samples, I have now that if-def calibration and end-if statement, and in between I first check if my calibration sample has become greater or equal calibration set. In that case I reset calibration sample to 0. And then I read into the actual element of my calibration data array a ADC value. In that case, the ADC value for current. And then, of course, I increment calibration sample. So calibration data is really a ring buffer in which I constantly read samples from my ADC. There's also an addition to the block where I usually display stuff every 100 milliseconds. My usual sprintf and serial print here is now preceded by an if not def calibration. But if calibration is defined, I do a calibration print of my calibration data and the size of my calibration set. That function, calibration print, gets the array and the array size as argument. Then I have here some local variables. First of all, a sample, which I use to loop through the data in the array. Then a 32-bit variable, a sum, which will contain the sum of all elements in the array. Then a 16-bit variables minimum and maximum, which will contain the minimum and maximum value within the array. They are, of course, initialized to the maximum and minimum values of a 16-bit integer. Then I have a float squares, which will contain the squares of the elements of the arrays minus the average value, which is of course stored in the float average. So yes, I will be calculating an RMS noise. In a first loop here over all samples, I determine the minimum and the maximum and also calculate the sum. With the sum, I can calculate the average value. And then in a second loop over all samples, I take each sample minus the average value, square that, and I sum up all the squares. as I said, I'm calculating the RMS noise. Finally, I print out the average, the noise peak to peak, so maximum minus minimum, and the RMS noise, so the square root of my summed up squares divided by the size of my set. That's it. Now let's calibrate. And now, let the calibration commence. Well, not exactly the calibration. We will still be looking at raw ADC values for now. But anyway, we'll start with the battery voltage measurements, because my lab power supply here, a linear one, is for now acting as our battery, also supplying power to everything. And I've looped in my multimeter here directly to the breadboard so we can get some real accurate voltage measurements. Okay, I think we can all agree for 20.00 volts, let's call that 20.00 volts, that our RMS noise is 0.8, 0.9, noise peak to peak 11, 12, and our average value, again averaged over 2048 samples, is 1341.7.8. Okay. For our second calibration point, 29 volts, interestingly, the noise went up again. So yeah, there's still some work to do with that switched linear regulator, getting the battery voltage down to 9 volts. But we can agree here that our value is between 3810.2.3, 0.2.3. I will review the footage afterwards. Our noise peak to peak, yeah, about 27, 25, up to 30 a little bit, and noise RMS about between 2.0 and 2.2. Oh, there's also 1.9. For the temperature calibration, here's our sensor. I'm using again a thermocouple together with my multimeter, which currently shows 23 degrees C. And whatever the multimeter is showing, I can't see it from here, we get a reading of 1827.7, steady, average over 2048 samples, or 0.6, okay, so it's fluctuating a little bit. Noise peak to peak, 12, 13, 15. Noise RMS 0.7, 0.6, I also saw 0.8. Great. The thing is, for a proper calibration, I also need to know what my voltage divider after my temperature sensor is actually doing. So we're first measuring the voltage here, if I can get it somewhere, at the output of our temperature sensor. 1.798. 1.798 volts. And then again the voltage at the input of our ADC, 1.121. Please keep these numbers in mind, okay? Finally, current measurements. My lab power supply here is only supplying current now to the current sensor, which is shorted out. And my multimeter is as an ampere meter in line with my current source. Power to the whole thing is provided by the auxiliary linear power supply here. Okay, we are at 0 amps. Our average value is 2043.5. And that is quite okay. Smack in the middle, it would be 2048. Peak-to-peak noise, 16, 15, 17. As mentioned, I'll review the footage afterwards. And RMS noise, 1.1, 1.2. Also not too bad. And now let's turn up the volume. 5.007 amps and value 2248.4. Yeah, 0.4, 0.3. Noise 16 peak to peak, 19 peak to peak, RMS noise 1.4, 1.5. Great. Here are the results. Basically the same table I've shown you 3 weeks ago, but with different numbers. We have a line for each calibration point, so for 0 amps, 5 amps, 20 volts, 29 volts, and today 23 degrees C. Then we have our average binary value, our noise peak to peak in LSBs, and our noise RMS in LSBs. And for all three, we have the minimum and the maximum values, which I observed watching the footage, the center value of min and max, and the difference between min and max. I also won't read out each and every value this time. Anyway, first I want you to note that the difference between our minimum and maximum average values is now well below 1 LSB. Second, the maximum peak-to-peak noise is now, with one exception, below 20 LSBs. The exception being our voltage measurement at 29 volts, where we saw a maximum peak-to-peak noise of 30 LSBs. Third, the maximum RMS noise is now between 0.8 and 1.5 LSBs, with the exception again of the 29 volt measurement, where we saw 2.4 LSBs. I already talked about that steep increase in noise for 29 volts during the measurements, and my best guess is that the switched regulator somehow goes into another mode at those higher voltages and produces more noise. Another thing to investigate in the future. Now, with those ideal resolutions of 40.96 LSBs per amp, and I told you 3 weeks ago it was 50 LSBs per amps, that was wrong, 273 LSBs per volt and 10 LSBs per degrees Celsius, these maximum noise levels translate into 0.46 amps peak to peak, 0.11 volts peak to peak, and 1.7 degrees Celsius peak to peak, respectively, as maximum RMS noise 0.037 amps RMS, 0.009 volts RMS, and 0.08 degrees Celsius RMS. Now compare that to the readings we got 3 weeks ago. So noise peak to peak is down an order of magnitude or more, while noise RMS is down in most cases almost 2 orders of magnitude. I'll say we spent the last 2 weeks chasing noise very well. Before we do the real calibration with the oversampled values, here are the code changes for that. So first of all, I have now 3 macros defined. First, calibration, which is still active. Then a calibration deck raw values, which I have commented out at the moment. And calibration binary. In the loop, I have now 2 different sets of calibration constants and variables. Here we have the constant and the variables for the raw deck values. The only change here, which I made also in the second set, is that our data array is now unsigned integer 16, of course, not signed integer 16. That was an error and it didn't matter as long as we were working only with 12-bit values from the deck. But now with 265 times oversampling, we are working with real unsigned 16-bit values. And then here I have the calibration binary for the oversampled values, and we're taking here only a set of 256 data points for our statistics. The raw ADC data is now only taken when the calibration deck raw macro is active. And in our display block, I take now when the calibration binary, so oversampled data macro, is active, oversampled data from our classes, currently from the current class. The rest is unchanged and it's still using the calibration macro to be activated. And in the calibration print function, I of course also changed everything to unsigned types. That's it. We start this time with the current calibration because everything is already set up for the current calibration. So we're looking here at the values for 0ms, obviously. And as you can see, it's very quiet. So a value of 32,696.0 or 5.9. Noise peak to peak 6 and noise RMS 1.2. Again, I will go over the footage afterwards. Now let's turn up the volume to 5.007 amps. And this can take a while until we get 265 samples. And here are the 265 samples. Again, noise peak to peak 6, noise RMS 1.3, and we have a value of 35,947.7.6. Great so far. Now for the voltage. As you can see, we're at 20 volts and our value is rock steady, almost rock steady, 21,453.52. Yeah, again, I look at the video footage afterwards. Noise peak to peak 4, 3, noise RMS 0.9. And now let's get up to 29 volts and wait until everything has stabilized again. Okay, value 60,974, about-ish, plus minus a few tenths of an LSB. Noise peak to peak 7.6, noise RMS 1.7. Now I'm very interested to see when that noise level, RMS noise level, is dropping down again. So let's take, that would be charging lithium iron phosphate battery. Let's go down to a full one with 27 volts. Okay, noise level is still quite high. Let's try 24 volts. Okay, noise level is dropping, so let's make one last stop at 22 volts. Okay, noise levels are, as for 20 volts. So it's definitely has something to do with the voltage. Okay, let's move on. And finally, the values for the temperature at currently 23 degrees Celsius. 29,296.4, 0.3, 0.5, 0.6, 0.7, 0.8, 0.9. Maybe temperature is rising? No, it's stable. Whatever. I will again have a look at the whole video. Noise peak to peak 5. It was 4 before. Noise RMS 1.3. Now 1.4, 1.5. So maybe things are really heating up. I don't know. The results are in same table format as before, only our numbers here are of course much larger because we have no longer 12-bit raw DEC values, but 16-bit 265 times oversampled values. Our maximum peak-to-peak noise values are down again. They are now about half to a third of what we saw before with the raw ADC values. If you take into account that our LSB resolution per unit has increased 16-fold due to the 256 times oversampling, our noise is now really low. Maximum RMS noise values stayed about the same. But again, one of the previous LSBs is now 16 LSBs. So in fact, they went down about a factor of 16. All in all, we have now for our current measurements a maximum peak-to-peak noise of 0.0092 amps and a maximum RMS noise of 0.00198 amps. For the voltage measurements, 0.0023 volts peak-to-peak and 0.00043 volts RMS. And for our temperature measurements, 0.0313 degrees Celsius peak-to-peak and 0.00938 degrees Celsius RMS. Now, let's put those calibration values here into our code and see what measurements we actually get. But before that, I have to make a confession. I wired up our temperature sensor completely wrong. I corrected that, of course, and redid the measurements for the temperature sensor. So that yellow line here are the new values and here down below are the old values. And of course, our absolute raw ADC values changed quite a bit with a working circuit. And our noise values are incredibly also a wee bit down. I did of course the same with the oversampled values, and again the absolute values have of course changed, but the noise values are still, well, let's say comparable. Maybe they are now a little bit higher. Anyway, I quite rushed through that, so don't expect too much from the calibration. With that out of the way, I entered the new calibration values here for our current class. And here for our voltage class. Please note I changed some types here from unsigned integer 16 to integer 32 because I became concerned that there were some overflows. Remember, our lower voltage, our 0 at the ADC is now 15. So in theory, we can get now negative offsets and such. The biggest change, of course, was in our temperature class. We no longer need that complicated calculation here for voltage divider with a temperature variable resistor and all the constants associated with that. Instead, we have now something that is quite similar to what we have in the voltage and the current class. Another little change, I multiply my scale here by 10, So we get now 10th of degrees out of here in a 16-bit integer, instead just full degrees. And of course, I only have two calibration constants here. My scale is fixed by the value in the datasheet from the sensor of 10 millivolts per degree C, and my voltage divider together with the resolution of our ADC. And the offset calculation is the same as for the current class and the voltage class. I'm also using here 32-bit signed integers now to avoid any overflows. Finally, I commented out all the calibration macros in our sketch. And here in the display portion, I format now my temperature as a floating point with 1 decimal before printing it out here. Okay, here we have our usual display, and we're doing the voltage measurements and the temperature measurements first. As you can see, our current measurement, if I go just by the display of my power supply, we're 40 milliamps off. Not good, not bad either. I would have liked it to be a little bit more precise, but we are spot on with our voltage measurement, at least for 20 volts. Our temperature measurement is 3 degrees off. I mean, this is not very precise here, but anyway, and I rushed through the calibration. So that's okay for the moment too. But now let's see if I increase the voltage, 21 volt. Yeah, we're spot on. 22 volts, spot on. And please note, all the measurements are really rock steady now. 23, yeah, spot on. 24, yeah, almost spot on. A little bit larger error. 20 millivolts, but then this display here is not that accurate. 25, okay, we certainly see here an increase in error, 30 millivolts, but still okay. 26, the error goes down again. 27, okay, spot on. 28, okay. Now we're really spot on again. And 29, our last calibration point. And yes, 10 millivolts off. But oh, did you notice that? We had a jump here in current, and obviously we don't have a jump here in current. A quite significant jump from 80 milliamps to 440 milliamps. Let's go down here again. That decreases enormously, and now we are at 27 volts, 26 volts, again at our initial value that we also had at 20 volts. You remember we saw also a jump in noise at some point when we increased the supply voltage over a certain limit. I wonder if these two effects are somehow connected, but that's for another video. But below 26 volts, everything works fine. Anyway, just out of curiosity, let's go down here, down 29 volts, 19 volts, sorry, yep, spot on, 18 volts, spot on, 17 volts. We see again an increase in error. And I think what that is a common mode error for our voltage differential amplifier. Again, maybe you remember, I told you that even with 0.1% tolerance resistors, we might experience a significant common mode error here. And yeah, that's it probably. 16 volts, yeah, that's error is going up again. So that's definitely supporting my common mode error theory here. And our current readings go down. I wonder if there's some kind of crosstalk between the voltage channel and our current channel. But again, that's for another video. 15 volts, our lowest, and there we have a large error, but that's not common mode error, but that's just hit our op amp hitting, or not quite hitting, the ground rail because of its headroom it requires at the output stage. Anyway, let's go back to, let's say, 22 volts. It doesn't matter. And how can we test if the temperature sensor is working? I mean, it's off 3 degrees, but let me go over to the board and blow a little bit onto it. Maybe we can increase the temperature. The sound will be awful. Sorry for that. Yeah, definitely working. Sound should be back to normal. That's just, yeah, a thing with the calibration. Perfect. Now let me set up everything for current measurement, and then we see if, well, our current channel is at least, you know, within 100 milliamps of the actual current. Okay, I set up everything again for current measurements. You saw that before. I shorted out my current sensor here. So the voltage readings are really just nonsensical. Don't rely on them. But we are interested now in the current, and we will use the display from my power supply this time. And it should be 0 amps, and we are clearly at 20 milliamps, but that's only an error of 2 LSBs. So nothing to complain so far. Let's switch that on. Yeah, nothing happens, of course. So let's see, 1 amp. And we are at 1.04 amps. Great. 2 amps, 2.03, 2.04 amps. Good. 3 amps, 3.03 amps. Also nice. 4.02 amps. Okay. And our last calibration point, and the most I can supply here, 5 amps. 5.03 amps. Okay. So about-ish 3 LSBs off. So I don't know if my dream, and if you remember, specified that I want a 100 milliamp resolution, and we are already there, okay? But it would be nice to have a 10 milliamp resolution, but that's maybe too much for a 12-bit DAC and the current sensor we are using. That's it for today. Quite satisfying results, with the one exception of that noise jump at higher supply voltages in conjunction with a jump in the current measurements at higher supply voltages. I'll guess I will have to analyze that stuff a little bit more in depth to see what's really happening here. Anyway, till next time, bye.